Okay, the first in a series of organic chemistry reactions to know is the free radical substitution reaction of alkanes. A little bit of other information about alkanes that you should be aware of, or that you may already be aware of, is that alkanes are fairly unreactive compounds. In terms of their chemistry, they may seem a little bit boring at first. They are only made of C's and H's, so they're hydrocarbons. Everything is single bonded, and that makes them nonpolar, which means they tend not to mix into aqueous systems or with anything else that's polar for that matter. So one of the reasons why they're a bit unreactive is that they just don't mix with other things. The other thing is that the carbon to carbon and carbon to hydrogen bonds are relatively strong bonds, and therefore they don't readily break and form new bonds because a lot of bonds aren't as strong as them. The major reaction that we use alkanes for in our world is combustion, something you would have covered during the energetics unit, which is reacting with oxygen to form carbon dioxide and water. Why do they undergo this reaction? Because the C to O double bond and the O to H bonds are even stronger covalent bonds than carbon to carbon and carbon to hydrogen. So it leads to combustion being highly exothermic and very spontaneous. The combination of properties, that is being pretty unreactive in general, but actually burning in oxygen readily and releasing lots of heat, makes them really excellent fuels. Means you can store them pretty safely in your gas tank, and yet when needed, they can be burned and produce lots and lots of heat for propelling you forward. They're better fuels than alcohols for the same number of carbons because they contain less oxygen, so they're less oxidized, and it leads to greater enthalpy changes per mole. So the ones that you'd be aware of are like natural gas, methane, propane, butane, octane. The actual one that gets used as petrol or gasoline is 2,2,4-trimethylpentane, and diesel, which is a much longer molecule, but it's also just a simple alkane. The other reaction that alkanes will undergo is in the presence of a free radical, and it's a substitution reaction. So a free radical, for those who haven't done it before, is a species with an unpaired electron. Okay. Note, this is not an ion. Okay? This does not mean that it's gained an electron or lost an electron necessarily. It's got an unpaired electron, which is a difference, and I'll try to distinguish what that is. In general, for this reaction, you're going to be dealing with a halogen free radical, either chlorine or bromine. And so what a free radical is, instead of being Cl minus or Br minus, which would be the ion, the Cl radical or the Br radical, usually you actually just draw it by putting a dot next to them to indicate that there is an unpaired electron. In fact, if we were to go back to our old dot system, it would look like that. A chlorine free radical actually has 7 valence electrons, but one of them is unpaired. Now, it doesn't have a charge because chlorine should have 7 valence electrons. That's the number of valence electrons that it normally has. But chlorine normally exists as a Cl2 molecule, which stabilizes it by sharing the pair of electrons between the two chlorines. Same goes for any of the halogens. So when a free radical is formed, the bond is split and they end up having this one unpaired electron. That's what a free radical is. It is not an ion, and the IB will be looking to see whether or not you know that, especially on paper 1. So the overall reaction for free radical substitution, the one you need to know, is that alkanes can react with a halogen molecule, so like a Cl2 or a Br2, and the net product is going to be a halogenoalkane and a hydrogen halide. Okay, so essentially what's happening is one of the halogen atoms in this halogen molecule is going to replace one of the hydrogens in the alkane. So let me go down one line. So one halogen replaces one hydrogen, hence the name substitution. One halogen substitutes for one hydrogen atom. To do a specific example, you would take something like ethane, and you'd add something like chlorine, and in the end you'd have C2H5, and instead of one of the hydrogens, you started with 6, now you have a chlorine. And where'd that hydrogen go? Well, now it's with the other chlorine, because you started with Cl2. So this is the overall net chemical equation for free radical substitution. Substitution is very useful. You know that you're going to substitute something. So you're going to substitute one of the halogen atoms for one of the hydrogens, and that's all that takes place. Now for SL, this is the one mechanism that you need to know in detail. For HL, it's one of many, but for HL, it's actually very similar to the ozone breakdown mechanism that you've learned in the past, which was also dealing with free radicals. So the first step is the creation of the free radical. The condition needed is ultraviolet light. Ultraviolet light is what splits the chlorine to chlorine or bromine to bromine bond. And so in terms of the mechanism, this step is called initiation because it begins the reaction. It's also referred to as homolytic fission. It's called that because when we split this bond, so lytic, right, meaning cutting, and fission, meaning breaking. So when we cut this bond, it's going to be cut in half, and each atom is going to get the same number of electrons. So the initiation step is as follows. You start with Cl2, you add some UV light, and afterwards you end up with 2 Cl atoms. Now you're welcome, if you want, you can at this point add in the dot to indicate that these are free radicals that we're dealing with. So that's the initiation step. On top of the arrow, if you wanted to, you could draw in a little UV symbol. U and V to show that it takes UV light, or you can draw HV from the energy of light equation, but I wouldn't really expect people to come up with that. At some point, you'd probably want to include that the condition necessary for this to happen is ultraviolet light. So there was a C to C single bond. Notice that bond has been split, and one electron has gone to this chlorine, and one of the electrons has gone to that chlorine, hence the name homolytic fission. So the first step of this mechanism we call initiation. It requires UV light, and chlorine is turned into 2 chlorine free radicals. Okay, so that was initiation. I will copy this step and we'll bring it down here. So the first step is that. The second step is that one of those chlorine radicals reacts with our alkane. We'll use the C2H6 example. And if you think about the alkane, the thing that's on the outside is the hydrogen atoms. So as this chlorine radical bounces into or collides with the alkane, the first thing it's going to hit is hydrogen, and it's going to rip off that hydrogen. What that does, though, is it produces yet another radical. It rips the bond between carbon and hydrogen in half and leaves behind one unpaired electron now on the alkane. And so this thing, the C2H5, is now a radical. So the reason why the second step is called propagation is because you start with one radical and you produce another radical, and that keeps the reaction going. So up till this point, we usually talk about reactions as single steps, but this is taking multiple steps to happen. So propagation is starting with a radical, ending with a radical. The termination step, there are actually many different termination steps that you could write. This is one of them, is that the C2H5 could react with the other chlorine radical that's perhaps still kicking around somewhere, and they would combine and make C2H5Cl. And so termination means that you have 2 radicals to begin with, but when they collide, they form something that's no longer a radical, and it terminates or ends the reaction. So these are the 3 basic steps of the free radical substitution. However, before I do the however, if you notice, when you add up these steps, the 2 chlorines have been used up. So the 2 chlorine radicals that you produced have been canceled out. They've been used up. And so this C2H5 has also been formed and then used up. So those all cancel out of the overall equation, and the Cl2, the C2H6, the HCl, and the C2H5Cl, that's what would actually show up in the final equation, and that matches the overall equation that we wrote up here perfectly. So the mechanism does add up to the overall equation. Now, somewhat contradictory to that, the IB really likes it. If they ask you to write out this mechanism, they usually want you to show more than one propagation step. The idea with free radical reactions is that for every termination step, usually thousands of propagation steps take place simply because they are more likely to happen. There's way more non-free radical molecules around than there are free radicals, so it's much more likely that a free radical would bump into a normal molecule than a free radical bumps into another free radical. So if you have to do that, the best thing to do is to take that radical that you formed, C2H5, have it bump into another Cl2, form C2H5Cl, that your kind of end product molecule, and form another chlorine radical. This is an especially good second propagation step to show, because what you're showing is that within the two propagation steps, you're just making another chlorine radical. And so if you think about these two steps happening back to back, they could just take out thousands and thousands of these C2H6s, because a chlorine radical reacts with one, and then the radical that it forms reacts with chlorine and makes another Cl radical. So when you get asked to show the mechanism, I strongly encourage you to give one initiation step. There's only ever one, and then two propagation steps, and then one termination step. The other thing to point out is that multiple termination steps are possible. It's also possible to make C2H5 plus C2H5, and that would make C4H10. So any two free radicals can end up colliding with each other and forming a non-free radical, and that is considered a termination step. You could also have things like this, where C2H5, what other termination could we do? Well, I guess technically you could have Cl plus Cl. It is theoretically possible that two chlorines could come together and form Cl2. Also possible this can this chlorine atom that you make here, if I want to get crazy and show you a third step, that chlorine could react with this. If this is still in the reaction container, there's no reason why that can't react, and you can form HCl plus C2H4Cl, and then that can go on C2H4Cl plus Cl2, C2H4Cl2 plus Cl. So I'm really going over the top here. This is far more detail than you'd need to give, but I only pointed out for one reason, which is to show that when you do this free radical substitution, it's not very good at producing just one product. This is not normally a reaction used in like the synthesis of a particular compound. If you notice, so far I've shown you that we could make this dichloro. We could make just the simple single chloro. We could also make butane. We could reform chlorine. So there's all sorts of different products that you could make. And so sometimes the IB as a follow-up question will ask you, what's a reason why there's low purity of the main product, which is the single chlorine being added, the chloroethane. And so probably the easiest is to point out multiple termination steps are possible. So multiple products are possible. And then you could also point out that chlorine can substitute multiple times on the same alkane, and therefore you can get things with one chlorine, two chlorines, three, four, as many chlorines on there as there were hydrogens originally. So those are just a little minor detail to realize at the end. If you were actually going to be asked this question, you would generally either be asked for what homolytic fission means, what the mechanism is in terms of initiation, just two propagation steps, not all these four, and then one termination step. And any of these three would be acceptable as a termination step. You should also know the overall mechanism, the overall reaction. C2H6 plus Cl2 makes chloroethane and HCl. And you should know that the condition needed to make the free radical is ultraviolet light. So I hope I didn't complicate that mechanism too much. Initiation, propagation, termination.